It's again a real pleasure to have Itai Arad speaking to us. Itai also, he did his PhD in physics and worked for a while in astronomy before he saw the light and moved to quantum computation. I think he's he was a postdoc initially with Dorit Aronov and then at Berkeley. And ever since those days, he's been singularly focused on this issue of area laws. And I think I can say that I know of nobody who's thought as long and deeply about this subject as Itai. So again, it's a real pleasure to have you here and talk about it.
Okay, thank you very much, Umar. Thanks for inviting me. Okay, let me first, can I share the screen now? Yes. Is it okay?
Yeah, looks great.
Okay. Okay, so thanks again, and thank you, Zef, for this very clear talk. I wish you set a very high bar for for the level of clarity. I'm not sure I'm going to approach it, but in any case, I'm going to talk today about area laws in many-body quantum physics, and why I think they're interesting, and some of the techniques and insight that can be gained by studying these things. Okay, so the talk will have roughly like 4 parts. In the first part, I will introduce what an area law is and why it is interesting, and I will repeat some of the things that Zef said about efficient description of many-body quantum states and why do we care about area laws when we talk about simulations. And then in the next part, I will describe one particular approach for establishing area laws, which is called the approximate ground state projector framework. And I will define what these objects are and why they are. I'll try to explain why they are helpful in trying to establish area laws. And then I will apply this framework, and I will show one particular application of that for the case of 1D systems, and I will demonstrate how it works. And then, time permitting, I will try also to sketch the construction of such AGSP also for the 2D case. It's a very recent result together with Anwar Anshu and David Cosset, and that gives an area law for a particular subset of 2D systems. Yeah. So, and just like Zef said, any questions, I'll be very glad to answer. It's good if you will ask questions, even if I get stuck in the middle of my talk. Okay. Okay, so let me just move this here. Okay. Okay, so the subject that I'm talking about is of course the setup is many-body quantum systems. So we usually in many-body physics, we consider usually n spins or qubits. And we assume that they are sitting on some d-dimensional lattice. This is a very common model for in condensed matter physics. And the Hilbert space of the entire system is, of course, the tensor product of the Hilbert spaces of the single particles. Here I focused on qubits, where the local dimension is 2, but I will later switch to general d-dimensional particles. And the dimension of the entire space then is 2 to the n, which is the tensor product of these local dimensions. And like Zef mentioned, we can define the main object of this talk is local Hamiltonian. This is an Hermitian operator that encodes the interaction between these different particles, and we write it as a sum of terms HI. Each one of them is an emission operator, and it acts locally on two neighboring particles. So for example, in this picture, it will be there will be a term here and a term here, etc., etc. So this is the main object that I'm going to discuss. And the state of the system, of course, like I've said, is a vector in this huge Hilbert space. And to describe it, if we want to describe it fully, we have to specify all the coordinates of all possible bases. So for example, if we have a system of 4 qubits, we need like 16 complex numbers in order to fully specify the state of the system. Okay, so what are the main problem that we are trying to solve here? So the main problem is to understand these systems, and this is a very hard problem because of the underlying exponentiality of this problem. So one thing we would like to be able to do, and is for example to understand the time evolution of the system. There is a missing imaginary I here. So time evolution of this, to solve the time evolution of the system, we need to solve the Schrödinger equation. And if we know the Hamiltonian of the system, then it would be the state. If we know the state of the system at time 0, the state of the system at time t will be given to us by this formula. And this is a linear formula in a matrix multiplication of an exponential tensor with an exponential matrix. So it's a very hard problem. And another place where H comes into picture is when we describe the thermal equilibrium state of the system. If we take our system and we attach it into a heat bath at temperature T, then we know that the state of the system is described when the system reaches an equilibrium, is described by this exponential matrix of 2 to the n and 2 to the n. It is called the Gibbs state of the system, and Z here is just a normalization constant. And if you want to understand the properties of the system at equilibrium, temperature T, then we need to understand the structure of this huge matrix. For example, what we will be interested is understanding, for example, the expectation value of some local observable. So imagine we have some operator A, which corresponds to some observable defined on these two neighboring particles. It could be the energy interaction between these two. It could be, I don't know, average magnetization, etc. So this is an operator which is non-trivial in the space of these two particles, and then it is tensored with the identity on the rest of the system. What we would like to understand is what is its expectation value, and if we're doing the time evolution of the system, then it will be this expression, and if we have the equilibrium state, then it will be that expression. In both cases, again, because the underlying matrices are exponential, these things are, on the surface at least, are very, very hard problems for us to solve. Okay, so why do we care about the ground state? The reason why we care about the ground state usually is because ground state describe the system, are a good approximation to the system when the temperature of the system goes to 0. Recall that the Gibbs state of the system is given by this formula. If we now write this operator here in its diagonalizing basis, we will get this expression here. And now, if we let t go to 0, then we see that all the different contribution from all eigenstates of H will die off, and we will be left with the dominant contribution, which is the contribution of the eigenstate with the lowest with the lowest energy. And this is why when the temperature goes to 0, the Gibbs state of the system, the state of the system at equilibrium, reaches the ground state. And therefore, if we want to understand the physics of the system at low temperature, then we better understand the structure of the ground state. So we can now, having said that, then we can now phrase this problem as the problem of, if we want to understand, of understanding the global minimum, which is this eigenstate of a system, of a set of a local quantum constraint. This is what Zeb said, because we can also write the ground state as the minimal, as the state that gives the minimal expectation value of this operator. And in other words, what we are looking for is a state psi that minimizes this sum of local terms. And in view of the CSP and Hamiltonian correspondence, this can be viewed as we are looking for the quantum assignment that minimizes the number of violations. So this thing here will be the violations of a global system, where all the violations are given by are violations of local constraints. Okay, so now we might ask ourselves, how hard is it to approximate the ground state of a many-body quantum system? Formally, we can write this as the following problem: given some local Hamiltonian on some lattice, on some graph, then what is the hardness of approximating the ground energy of this system to within, say, 1 over poly, where poly n where n is the size of the system, the number of particles. So generally, this is known to be a very hard problem. It is in fact a quantum NP hard problem, or a QMA, as was shown by Itai in '98. Essentially, what it means that in order to solve this problem, this problem can be verified using a quantum witness. So if you have a quantum computer, then you know you can verify that a certain state is indeed the ground state simply by measuring its energy and then seeing that indeed this energy is below a certain threshold or not. So in general, this problem is shown. This is what Itai showed. This problem is extremely hard. It is believed to be harder than NP problems because the class of quantum NP is believed to be much bigger than the regular NP. However, sometimes for certain classes of problems, and this is the classes that I will try to talk about in this colloquium, this problem might be easier. Sometimes the problem of approximating the ground energy or approximating the ground state itself can be within P or within NP. And one reason why this can happen is when we have a classical representation of the ground state instead of a quantum representation. If we have a classical representation and we can manipulate this representation efficiently in a classical computer, then we can then maybe this problem is inside NP, because this classical representation can be the witness and can be the proof for certain properties of that system. Okay, so what is an efficient representation? So this is something that Zef has already mentioned. So generally, we have no hope of having an efficient classical representation of a many-body quantum state. And the reason is that generally, if we have a state over n spins or n qubits, then its general state should be written like that. And this is a collection of 2 to the n complex coefficients. And of course, we don't have enough memory in any computer just to store this thing. So, however, but it can happen that for certain classes of states, there exists some efficient representation of these states. And this is exactly what we mean by efficient representation. We actually demand the following 2 properties. The first property would be that we would be able to store or approximate or store the psi or some sort of an approximate description of psi using only a polynomial number of parameters instead of this exponential number of parameters. So that's one requirement for a representation to be efficient. The other, and not less important property, is that we demand that this way of storing the information will also be useful for us. In other words, what we actually demand is that we can take this representation and efficiently use it in order to approximate local expectation values of that state. In other words, we can use this representation to do calculations and to know things about the overall system. So, these two requirements represent what an efficient representation is, and and one way in which one route in which we can proceed in order to find efficient representations of many body quantum state is by bounding the amount of entanglement inside these states. So so why do we need to bound the amount of entanglement, or why does it help us to bound the amount of entanglement? So first of all, let me just remind you that entanglement can be viewed as some sort of a quantum correlation. It's a correlation between the different quantum particles, quantum degrees of freedom. And to demonstrate why having a bound on the entanglement might be helpful for finding an efficient representation, let's look at two very extreme cases. In the one case, let's look at a system of n particles, but let's assume that all these particles are unentangled to each other, and the overall state of the system is a product state. Okay, in such case, psi, the overall state of the system, can be written like this. And because each one of these psi I is a state in a local Hilbert space, then it can be represented by it can be represented by a very small number of parameters. So in order to fully specify the state of psi, we only need n we only need to specify n such psi, and so overall the number of parameters that we need is only linear in the system size. On the other hand, as we just saw, if we have a fully entangled state, then in general we have this superposition of an exponential number of states, and we will need something of the order of 2 to the n parameters just to specify them. Okay. So one way to find an efficient representation is by bounding the entanglement. And to bound the entanglement, then one way to do it is by establishing an area law. So what are area laws? So area laws are some sort of bound on the amount of entanglement that there is in the system. So imagine a system of particles that sit on some lattice, and let us look at a bipartition of the system into some region L and its exterior LC. Now, for any state in that system, say a state of psi, we can always write it as a superposition of states that are defined inside L. These are the I alpha inside, and time state that are defined outside of L. This is the O alpha. And we can also do it in a canonical way, which is called the Schmidt decomposition. And the Schmidt decomposition is actually the way that uses the minimal number of such product states. Now, when we write it this way, then also one of the properties of the Schmidt decomposition is that these weights here, this lambda alpha, if we take the square of them, they sum up to 1. So we can look at them as some sort of a probability distribution. And using this probability distribution, if we look at its Shannon entropy, then this defines us the entanglement entropy between L and its exterior part. So by having, for example, a flat distribution, then this means that we actually have a lot of our superposition consists of a lot of product states between the inside and the outside. That means that there is a lot of entanglement. On the other hand, if we just have a product state, then we will have only a single lambda, and it will be equal to 1, and then we have a sharp probability distribution, and as a result, the entanglement entropy will be equal to 0. Okay, so entanglement entropy is some sort of a measure, just like the number of these product states, that measures how much entanglement there exists between the inside and the outside. And an area law is a situation in which for every bipartition of the system into L and LC, we have that the entanglement entropy scales like the size of the boundary between these two things, instead of the more general situation in which it scales like the volume of L. If we take a random state and we will calculate its entanglement entropy, we will see that it will scale just like the volume of L. But in very special situation, this is for very specific state, we can there will be some states for which the entanglement entropy will scale like the boundary. And the intuition of why these things happen is that because entanglement can be viewed as some sort of a correlation between quantum degrees of freedom, then having an area law is some sort of a hallmark of locality. What it means is some sort of a toy picture to view is that all the correlation in the system are short range, and as a result, if the entanglement between L and the exterior of L measures the amount of correlation between the degrees of freedom here and the degrees of freedom outside, then only the degrees of freedom of L that are near the boundary will be entangled with the degrees of freedom of the outside part. And as a result, the amount of entanglement will be proportional to the size of the boundary. On the other hand, when the correlation are long range and there is all sorts of entanglement, all sorts of length scales, then we expect that different points inside the bulk of L will be entangled with different points in the bulk of LC. And as a result, the amount of entanglement should scale like the bulk of L, the volume of L, instead of the boundary. So area laws can be viewed in some sense as a sign of locality in the system. Are there any questions or? Okay. Okay. So so now that I have defined the area law, let me now state what is the conjecture, what is the AreaLaw conjecture. And the AreaLaw conjecture states that ground states of local Hamiltonian under certain conditions satisfy an area law. And this is a very strong conjecture because it tells us that the entanglement entropy in certain ground states of many-bodied quantum system is very, very restricted. And that will imply, in some sense, that it might imply that there exists some sort of an efficient description of these states. So specifically, what is the assumption that we are making here? So first of all, we are talking about local Hamiltonians that are defined on some well-structured d-dimensional lattice. So it can be three-dimensional lattice like this, or two-dimensional or one-dimensional, and we assume that the interactions are between nearest neighbors, just like I drew here in this picture. This is the first assumption that I'm assuming, and the second assumption is something that might look strange in the beginning. It's an assumption about the eigenvalues of this operator H, or the eigenenergies of the system. What I demand that there is a gap between the lowest eigenvalue of H, which is called the ground energy, and the first eigenvalue that comes above it, which is called the first excited energy. And we define this gap to be to be the difference between these two energies. And the AreaLaw conjecture states that whenever we have a large gap, so whenever the difference between these two energies is of order 1, and the overall Hamiltonian has these properties, so it is short range, sitting on the lattice, etc., then the conjecture states that the ground state of that system should satisfy an area law.
Sorry, can I ask a question?
Yes, sure.
When you say that it's order 1, you mean it's lower bounded by a constant, or it's upper bounded by a constant?
It is lower bounded by a constant.
Oh, I see this. So this is what a CS person would write as omega.
Oh yeah. Sorry. Yeah. You're right. It should be an omega. Yeah.
Okay. Thanks.
Yeah.
So while we are clarifying, Itai, did you mean delta times epsilon, or you meant something else there? Did you just mean delta, or?
I just meant delta. Yeah, it's a typo. Delta is the order one. Yeah. Okay. So why do we think that this conjecture is true? So here is one intuition I like. Large spectral gap. It implies a fast convergence to the ground state, and therefore it implies that the ground state has a weak correlation, and as a result, it doesn't have a lot of entanglement. So specifically, one way to view it is that we can look at this operator. What this operator here will do is that it will scale every eigenstate of the Hamiltonian with 1 minus the energy of that eigenstate divided by the overall norm of the system. And as a result, this operator will, if we apply it L times, it will take us to the ground state. Now, the speed at which it will take us to the ground state depends on the gap between the ground energy and the first excited state. The larger the gap is, the faster we will have this convergence. Now, intuitively, if we are converging very fast and we are starting from something that has no correlation at the product state, then it also means that the target, the fixed point of this map should not have too much correlation. So, so this is one intuition why the existence of a gap is an important thing for establishing an area. However, it turns out that taking this intuition and turning it into a rigorous theorem is not a very simple thing to do. And so far, it has only been established generally and rigorously only in 1D, and this was first done by Matthew Hastings in a breakthrough result from 2007, in which he showed that if we have a one-dimensional system, so here it will be just a chain of spins sitting or qubits sitting next to each other, and there is a local Hamiltonian that acts on nearest neighbors. And in this case, if we bipartite the system into two parts, so we have the part here and the part here, and we measure the entanglement entropy between these two parts, then the entanglement entropy will not depend on the size of the bulk of one of these parts. It will only depend on the size of the area of the cut between them, and in 1D it's just a constant. So therefore, the area law in 1D would imply that the entanglement entropy should be bounded by a constant, and this is precisely what Hastings did. Sorry, here again it should be just delta, not delta E. He showed that if the local dimension of the particles is D, and the spectral gap is delta, then the entanglement entropy is bounded by this constant. It is the exponential of log D divided by the spectral gap. Actually, Hastings proved more, and from his proof, we not only were able to bound the entanglement entropy, but we could bound also the other Schmidt coefficient, the other coefficient in every bipartition of the system. And as a result, Hastings could show that for such ground state, there is always an efficient description using a polynomial tensor network. In this case, it would be this matrix product state, this one-dimensional comb-like tensor network that Zev showed. And as a result, the problem is inside NP because, well, we can just give you this this tensor network as a proof, and you can use it to do efficient calculation and convince yourself that indeed the energy is what I claim it is. Okay, so so that was Hastings' breakthrough in 2007, and ever since there was a thread of works that improved his result or tried to push to more general directions. So let me just give a very brief list. Together with Alexei Kitaev and Zev and Umesh, we proved in 2013 we had an alternative proof for the area law using the AJSP framework, which I will explain soon, and in which the bound on the constant of the entanglement entropy was improved significantly. So instead of having an exponential, now it is only a polynomial of the d and the delta parameters. Another interesting result is by Bandaue and Rodetsky from 2013, and they showed that at least in 1D systems, it is enough to have some sort of a decay of correlations in order to prove an area law. And finally, Zev, Thomas Vidik, and Umesh, they managed to also to show that in 1D, it is not only that there exists an efficient classical description for the ground state, but that this description can also be efficiently found classically using a polynomial time algorithm. So that means that the problem of approximating the ground state is not only an NP, but it is actually in P in 1D. Going on to 2D, then here we still don't have a proof for the general case, but there are some exceptional things that we can do under further assumptions. For example, Hastings and Massans, they proved that if the spectrum has a sub-exponential number of excitations, then one can show an area law in more than 1D. I'm sorry, don't know how to say this name, Osborne and Isert, in 2010, they proved an area law for a system in which the Hamiltonian is frustration-free and is made of two local spin-half systems. I will discuss. We'll discuss a little bit further what frustration-free systems are. Michaelakis showed that if you have some sort of adiabatic assumptions on the path of Hamiltonians, then you can also prove area laws in higher dimension. And Kao in 2014 used some sort of local consistency and overlap conditions between different parts of the system in order, again, to establish a 2D area law. And finally, there is this very recent result that I hope to get in the end of this talk by Anurag and Anshu and David Doucet, in which we show that if the system is frustration-free and has another stronger than a gap, but a local gap condition, then we can also prove an area law. Okay. So this was the first part. This was the introduction for what is an area law and why it's interesting. And now let me try to explain one approach for proving the area law using the approximate ground state projection framework. Okay. So let's recall what the problem is that we are trying to solve. We have a system that is defined by a local Hamiltonian, and we have its ground state, and we have some bipartition of the system into L and into the other part of the system. And using this bipartition, we can write most generally we can write down the ground state as a superposition of product states between L and its external part. And this decomposition defines to us some sort of probability distribution. These are the lambda alpha squared, and we want to show that in some sense this probability is sharp. It's peaked on very few values, and then it decays very quickly. Okay, so therefore the entropy of that probability is relatively low. So specifically what we want to show that morally that the number of non-vanishing coefficients in this state scales something like exponential of the boundary of this region L. So this is more or less the mission that we are set to solve. Okay, so so how can we do that? So let's first assume, without loss of generality, that the ground energy is 0. We can always scale the energy of the system by adding a constant and not changing anything. So in that case, if we go back to this first intuition that we have, we can look at this map that takes any state and pushes it toward the ground state simply by rescaling every eigenstate in its decomposition, every eigenstate which is not the ground state, by scaling it by some number which is smaller than 1. And therefore, if we apply it more and more and more times, we get closer and closer and closer to the ground state. Now, instead of applying it, if we want to show an area law, what we want to show is that this guy, the ground state, doesn't have a lot of entanglement. So, but every application of this operator here can create more and more entanglement. It can create more and more superpositions of parts from the inside and the outside. So one way to proceed is, instead of starting from an arbitrary product state, let us start with a product state that is made of 2 states. One state is defined on the inside. This will be I1, and one state is defined on the outside. And let us start, and let us take as a starting point the product state that has the largest overlap with the ground state. And one can show that this is actually the first product state in this expansion, in this Schmidt decomposition. And let us take this state to be the starting point of this mapping, and see how many times we have to apply this map before we can start filling the ground state. So if O1, if we now try to expand O1 times I1 in terms of the ground state and anything that is perpendicular to the ground state and will be killed by this map, then the overlap, then the coefficient between the ground state will simply be the overlap of this product state with the ground state, which would be λ1, and the rest will be something which is by definition perpendicular to the ground state. Therefore, if we now take this mapping here and we apply it L times to this product state, we ought to get something like λ1 times times the ground state, plus some error that will go down the more we apply this map. Now, this operator here, it is some sort of an approximation to the projection on the ground state. It is not exactly the projection because it doesn't kill anything which is perpendicular to the ground state, but it shrinks it a little bit, and therefore it is just an approximate projector. And it is this type of object that we will be using in order to establish an area law. Okay, so how can we use this type of object? So generally, let us assume that we have this this type of some sort of an approximation to the ground state projector, and and therefore, when we apply it on the product state with the large overlap with the ground state, O1 and I1, we get this overlap with the ground state plus some sort of an error. But the question is, in order for us to be able to say that this is a good approximation to the ground state, we have to realize how important is this error here. So this is one question that we must first understand in order to be able to analyze this state. And the other question is, how much entanglement is there in this state? We started with something that has no entanglement, it is a product state, but then we applied this approximate ground state projector, and it can create some entanglement between the inside and the outside. So how much entanglement is there? So to answer these two questions, we need to characterize our AGSV, and we do that using two numbers, which are called D and delta, and they do precisely answer these two questions. So first thing, we require that the HSP, one thing I didn't say, but we can now require, is that it will preserve the ground state. So on the ground state itself, it acts like exactly like a projector. It preserves it. And then, in order to characterize how large is the error, what we will do, we will use this parameter delta that tells us what is the distance, what is the operator norm of the distance between our operator k and the exact ground state projection. So delta is tells us essentially how good this HSP, how close is it to the ground state projector. And in order to understand how much entanglement this guy is creating, let us we define this parameter. Sorry, we define this parameter. Sorry. Sorry. Okay. In order to understand how much entanglement this guy is creating, let us look at the minimal number of superpositions of operators that are acting only on the inside and only an operator that acts only on the outside. And let us look on the minimal way in which we can write k like that. And then the number of such terms in the superposition will tell us how much entanglement this state creates. Because if we act with this state on the product state, then we will end up having at most a superposition of at most d product state. So the two important parameters are d and delta. And if we have such an AGSP and we know it's d and delta, then if we act on some product state with this AGSP, then we know that it will give us some weight on the ground state plus an error that scales like delta. And if we act on it L times, then the ground state will remain the same, but the error will keep on shrinking. So now we ask ourselves, okay, so we can now create states that are getting closer and closer and closer to the ground state. But how large should this L be in order for this thing to be a good approximation of the ground state? And and the idea is that for this thing to be a good approximation to the ground state, what we need that the error, which is of order of delta to the power of L, should be much smaller than the weight of the ground state. If we manage to find such a delta, then we can write that the ground state is given by this is approximately given by this formula. And since we know that the number of product states in this expression will be d to the power of L, then we know that the overall entanglement of the ground state will be bounded by log of d to the power of L. But the question is, what is lambda? Because what is lambda 1? Because it is exactly lambda 1 that tells us how big this L should be, and this L exactly tells us what is the entanglement entropy of the ground state. So without knowing lambda 1, this whole program is useless. So this is where the bootstrapping lemma arrives, and this is actually the focal point of this approach. And what it tells you that if you manage somehow to construct an approximate ground state projector with parameters d and delta that satisfies this inequality, so that the product is smaller than 1/2, then this necessarily tells you that lambda 1 is lower bounded by 1 over square root of 2d, and as a result, you then use this type of argument, and as a result, then you can now prove that the entanglement entropy of the ground state should be bounded by an order of log d. And to prove this, the proof of this theorem can be it is few lines. There is some sort of a sketch here. One way to see it is that, you know, you can start from an unentangled state V, which is just a product state of something in the inside, of the outside and the inside, and apply an AGSP K, and you get some state W, and now W, because you pushed it closer and closer to the ground state, so now it has a larger overlap with the ground state. And in addition, you know that it is only made of at most D product states. So because now D times delta is smaller than 1/2, then you can prove that at least one of these pieces, one of these product states has a bigger overlap than V. And then you can go back here and apply it again and again, and this process will converge, and it will converge until the overlap is of the order of 1/2 squared of D. So this is one way of showing that if you have this good AGSP with these two favorable parameters, then you can prove an area law. So what this all tells us is that in order to prove an area law, all that we need to do is to construct an AGSP, an approximate ground state projection, with the good parameters D and delta. Okay. So the overall plan now is first find a good AGSP. So find a K with these parameters D and delta, such that their product is smaller than 1/2. This will tell us that the entanglement entropy of this region will be smaller than log of D. And if it happens that the D in the AGSP that we found has a bond dimension which is only exponential in the size of the boundary, then we are done, because that will imply that the entanglement entropy is smaller than the size of the boundary. But then, of course, the question is, how can we construct good AGSPs? Are there any questions so far? Okay. Okay, so this is the third part of constructing good AGSPs. So in order to, so now I'll start making a lot of assumptions, and I'll be even less rigorous than I was before. So, but this is just in order to make things. I will try just to pass the overall structure instead of focusing on the details. So I will now first assume that we are now dealing with 1D systems. So our Hamiltonian is defined on a chain of qubits sitting on a line with nearest neighbors interactions, like the interactions I drew here. And we are interested in bounding the entanglement between the left part and the right part. I will also assume that the Hamiltonian is frustration-free. What this means is, it means that the terms of the Hamiltonian are all positive or non-negative, and the global ground state of the system is also the local ground state of each one of these terms. So it is inside the ground space of each one of these local terms, so that the global ground state does not frustrate anyone locally, because it is for each and every local term, it is also their private ground state. So this is where the name comes from. And if we actually assume that we are in a frustration-free situation, then we can go even further and assume, without losing any generality, that the local terms here are just projectors, as long as we are interested in the properties of the ground state only. So this will be my assumption, that the local terms are projector. And in addition, I will also assume that we are locally gapped. What that means, it means that if I now look at part of the system and I look at the Hamiltonian of that part, so I'm looking at the sum of the HIs that are defined on the particles in that segment, then also that Hamiltonian has a spectral gap, and it is bounded by below by some constant delta. So this is This is the assumption of a local gap or a uniform gap, if you wish. So it means that not only the global Hamiltonian has a constant gap between the lower, the ground energy and the first exchange, but this happens also locally at every continuous patch of the system. So having these three assumptions, let us now first, let me just remark that for the proof of the 1D, all these assumptions except for the 1D assumption are not necessary, but they will make our life a bit simpler, so that's why I included them. So let's first let's do the first attempt in trying to construct an approximation for the ground state projector. So the first and most obvious attempt would be just to use this good old 1 minus h to the power of L. This thing leaves the ground state invariant, and it shrinks every other eigenstate of the Hamiltonian by a small amount. However, if we now try to analyze what is the what are the d and delta properties of this Hamiltonian, you will notice that the delta, so the amount of error that happens here, is something like 1 minus the smallest eigenvalue of the system, or the difference between that eigenvalue and the ground energy, divided by h to the power of L. In other words, we get this, the worst behavior happens when we look at the first excited state, and this number is pretty bad because it's not small at all. It's very close to 1 actually, because h is the norm of the Hamiltonian of the system. It can be very large, it can be of the order of n, and delta can be quite small. It can be 0.1 or something very small. So altogether, this thing is not a very small quantity. And on the other hand, if we try to analyze the d parameters, so how many product state applying this operator creates, then we can do it by writing h as a sum of all the terms that act on the left side, plus all the terms that act on the right side, plus this term here in the middle, which is called h mid. And one can easily show that the amount of entanglement, or the number of product states that are created this way, is huge. It is something like d squared plus 2 to the power of L. And in all situations, this d will go to infinity much faster than this delta will go to 0. And as a result, d times delta will be much larger than 1. So that means that this construction is not good, is not strong enough in order to give us an area law. Okay. Are there any questions? Okay. Right. So let us try something else. So I will now add another ingredient to the discussion, and this ingredient is called the detectability lemma, which is some useful lemma that applies for the ground states of frustration-free Hamiltonians. And essentially, what this lemma tells us, it tells us that if we want to approximate the projector on the global system to the ground state, then we actually can do that by patching together local projectors. So we can divide the system into segments, like the 5 particles here and the 5 particles here. We can take the projector to the local ground space of these particles, and then we can have, a projector to the local ground space of these particles and these particles, etc. And if we take the product of all these projectors, then we get an approximation to the global ground state. And the quality of this approximation depends on the overlap between these projectors. So if the overlap is of the order of m, so the radius of the overlap, then what the detectability lemma tells us is that and as long as there is a gap in the system, then it tells us that the product of these local projectors, is a good approximation to the ground state. It is good in the sense that it decays exponentially. The error, the difference between these two operators, the operator norm, decays exponentially in the length of m. So so we can approximate the global projector by small pieces as long as we have a gap. So now we can try and give a second attempt at building an AGSP. And the idea is now that if we want to build an AGSP that will bound the entanglement across a particular cut, then maybe what we can do is we can write down or approximate the ground state projection, not by h to the power of L or something like that, but instead make it a product of three projectors, the projector to the ground space on the left, the ground space on the right, and then a local projector here in the middle. So our candidate now looks like this projector of three, this product of three projectors. And now, if we do again this analysis, we see that this is still no good. Why it is not good? Well, because the delta, so this is the error, it will be just what the detectability level tells us. It will be something which is proportional to the overlap, which would be of the order of m. However, the amount of entanglement, because now the left side and the right side do not create any entanglement between the left and right because they only act on one side. But what creates entanglement is pi mid, the projector in the middle. And because it is defined on m qubits of order of n, one can only bound its entanglement entropy using something which is of the order of d to the power 2 to the m, because it is supported on d particles. And as a result, again, we're in the same business where for any realistic in any realistic situation, the pace in which d goes to infinity is much stronger than the pace at which delta goes to 0. And again, d delta is much bigger than 1. So this construction is still not giving us a good AGSP. Okay, so but there is a purpose why I gave this construction. And this is the third attempt. So in the third attempt, what we will do is we will look at this middle guy here, and we will try to tackle this problem here. Instead, we will try to replace it with something that maybe creates less entanglement. So this is what this figure here tries to describe. So instead of using the projector to the local ground state here in the middle, what we will do, we will try to approximate this ground state using some polynomial of the Hamiltonian of the terms in this segment here. So for example, we might try to approximate it using this type of thing, using taking 1 minus h middle divided by its norm to the power of k. We know that this thing, again, it shrinks everything which is perpendicular to the local ground state, and it preserves the ground state. So it is some sort of an approximation to the ground state. And as we will see, it also creates less entanglement. So maybe we can use this thing, or more generally, maybe we can take any sort of a polynomial that will approximate the projection here. And it turns out that the best polynomial that will give us the best approximation for a given degree is the Chebyshev polynomial. So if we want to approximate the projection to the ground state of a certain Hamiltonian, the best thing we can do if we want it as a function of this Hamiltonian is simply to use the Chebyshev polynomial. And the intuition is that the Chebyshev polynomial is in some sense very uniform. So if we scale it such that it will preserve the ground state, then you can see that because of the way it fluctuates, then it will kill in a uniform, it will shrink in a uniform way all the energies in a certain range. Whereas if we are instead looking at the 1 over something like 1 over x, then this then this thing will have very will have very strong effect on the high energy, but will not do anything on the low energy. So in that sense, the Chebyshev polynomial is a much better way of approximating the ground state. And indeed, it is used in many places in approximation theory and also in computer science for approximating step function, and the projector can be viewed as none other than a step function in the spectral space of the Hamiltonian. So if we take this together, then we then a Chebyshev polynomial of degree L, we can see that if we apply it on the Hamiltonian, if we rescale it properly and apply it on the Hamiltonian middle, it can give us an approximation of the projection to the attempt, which with this type of error. But then the question is, okay, so we did that. We now approximating this guy instead of using the exact projector. But why? How can that save us? How can that give us less entanglement? And here is the second idea, and this is the idea of entanglement amortization. And the idea is that if we now look at t to the L of h mid, this is essentially a bunch of terms like that. It's taking these local sums of hi and taking it to the power of L. And the idea is that this type of expression creates much less entanglement than one can naively think. And the reason why it creates less entanglement is that if we now open up this expression where we can see that it will be the product of different h's at different places. And if we focus on one such term, then we can see that there must be one cut in which there will be, in which there ought to be at most L divided by m terms if there is, if the degree is at most L and the number of terms here is at most m. And so we can always estimate the entanglement in that cut, and then we can, from that cut, we can also deduce the overall entanglement in the middle. So the overall conclusion from this is whenever we have a power of a local Hamiltonian, the amount of entanglement it creates is much less than L, and in fact it is given by this expression here. So it is L divided by m plus n instead of just d to the power of L. Therefore, if we take L to be m squared, we can get that the amount of entanglement is just something like m. And if we put it all together, now we can see that the operator, the approximate ground state projector that we get by taking this local Chebyshev in the middle and these two projectors on the outside will give us these two d and delta, and as a result, it will give us. We can then play by taking m to be of this size. We can always get that d delta is smaller than 1/2, and this is essentially the way that the AreaLaw in 1D is proved in the 2012 paper. Okay, are there any questions? How much time do I have? I think I'm sleeping.
I think we are pretty much, it's after 12, so you should be close to wrapping up.
Yeah, just two more slides, I guess. Something like that.
Yeah.
So,
okay, sure.
Okay, so let me just give the very brief idea of how this can be even further improved in order to prove the 2D AreaLaw. So in 1D, what we did was to use the Chebyshev and to approximate the ground state projector, and it gave us this type of approximation. And in order to do better, we need a better AGSP in order to prove the AreaLaw in 2D. And then, one natural question to ask is whether we can find a better polynomial than the Chebyshev. So generally, we cannot. But it turns out that sometimes there are some circumstances in which one can do better. And for example, there is this famous paper by Jeff Kahn, Nati Linal, and Alex Sandowski that says that that in the case of polynomials over bits, for our case, it will be the case where the eigenvalues of H are integers. Then actually, we can instead of having this type of error, we have this type of error. So it's like the square of what is written here. So it is a much better thing. And this motivated us to try and find better constructions stronger construction in which we may be able to imitate this behavior. So the idea, and this is really just skipping, the idea is essentially to take what we had before, but now instead of diluting just one projector, we will dilute a bunch of these projectors, and we will look at the detectability lemma made of these diluted or approximate projectors. And as a result, there will be much less entanglement. However, because now each one of these things is not a real projector, but only an approximate to the projector, we will have errors from different sources. So we will need to be able to take care of errors that happen at different sources. So in order to do that, what we did was to follow the construction of a robust polynomial by Shetov that originated from the problem of, suppose we have a bunch of noisy qubits and we want to approximate the end function of these noisy qubits. How can we do it in an efficient way, by taking care of different errors that happens at different places? And it turns out that one can define such a polynomial that does this approximation. So if every qubit is a bit noisy, so it's not exactly zero, it can be something between 0 and epsilon, then we can still write down a polynomial, a multivariate polynomial. So now it's not a single variable polynomial, a multivariate polynomial, and it will give a very good approximation of the end function. And what we did in the paper was just to take this polynomial and try to convert it into a polynomial in operators, and then apply it to these diluted operators that make up the AGSP. So overall, the structure was, start with the diluted Chebyshev polynomials, combine them together using this robust polynomial into larger blocks, and then do this process again and again and again. So what you get is some sort of a renormalization group flow. So you get bigger and bigger and bigger approximate projectors, and it turns out that this multivariate polynomial approximation can actually get you something much stronger than the plain Chebyshev polynomial. And in the 2D scenario, what we did was exactly to apply this construction along the cut. So we have these guys here. There are some overlap together with them, and essentially this is the AGSP that could make the job in the 2D setup. So this is the theorem that we were able to prove. And let me just wrap up. So in summary, let me just say that AreaLaws are the key to understanding the computational complexity of many-body quantum system, and the combination of the approximate ground-state projector framework with techniques and results from computer science and approximation theory gives us very powerful tools to analyze the ground state and ground space and in general low energy states of many-body quantum systems. And of course, there are still many open questions and many open problems. For example, can we relax the conditions that we use in the 2D proof, like the local gap or the frustration freeness? Can we make it a general proof for the 2D case? can we generalize it to 3D or 4D? This is not clear because in some sense we use the fact that the cut in 2D is one-dimensional. And also importantly, can we take this result and, just like in the 1D case, prove that there is an efficient tensor network, a tensor network that approximates this ground state? And finally, even if we did that, can we use this tensor network in order to and contract it efficiently in order to be able to do calculation with that? So in other words, these two things ask whether we can find efficient representations also for 2D ground states. And I think the grand plan here is that if we manage to prove this thing, then the global picture would be that the complexity of this type of systems of quantum spin system, their ground state on a d-dimensional lattice with nearest neighbor interaction and a gap, then it is essentially classical. It will be inside NP. It will have a classical description, an efficient classical description. So at least from that point of view, these systems are in some sense classical. Okay, so thank you.
Okay, well, great. Thanks, thanks, Itai.
Thank you.
Let's see if there are any questions. Norbert Schuk is asking why NP.
Why NP? Because then if you have an efficient description, I mean, if you manage to show an area law and you manage to show that there is a tensor network that describes these states, and you can use this tensor network in order to do calculations, then this tensor network, it can serve as a classical witness. So the problem becomes NP.
I missed the last point. Sorry. I see.
Okay.
Could it actually be easier in 3D and 4D than in 2D? Because at some point monogamy should kick in, right? If you go to high dimensions, you could imagine the problem is easier, maybe.
Yeah.
I mean, proving the area law. Could this happen? Or I mean, from your attempts?
I didn't try it, but it's a good point. You're right. Yeah.
Oh, that's very interesting.
Intuitively, yeah. But you know, I guess that in order to prove it rigorously, you will really have to take the very large dimension limit, right? I mean, it's
well, you could try to approach it from very high dimensions, and maybe you meet in the middle and whatever.
Okay.
Okay.
Very nice. Are there any other questions?
Yeah, can I ask? I'm confused about how strong this local gap condition seems to be. Yeah, so I guess.
Well, it's strong enough that we cannot lift it.
Okay, for the moment.
Yeah.
But do we know of any? I mean, of course, knowing of systems that have gaps in general is hard to sort of have a stable of examples. But do we have examples where we know there's a global gap but no local gap?
I think Anurag is here. I mean, he's the wizard of all these kind of content. So he has this kind of an example. Anurag, are you around?
Oh, hey. So I don't. So our assumption is more like for all the rectangles or squares on the lattice. So for that, there are no such examples. But you can have examples where you have a square lattice, and if you have a tilted square within the square lattice, then you can lose the local gap assumption there. So we don't require such subregions.
Sorry, so you know of an example where if you use a tilted square, you can sort of not have a gap, but
yeah, so you can have a gapped system on a square, but then you have a tiny square inside which is 45 degrees tilted, then you won't have local gap there. But we don't use such systems.
And does local gap, sorry, does local gap doesn't guarantee global gap unless you sort of, unless local gap does mean also taking the full square. Is that right? Or is that not right?
I think
No,
local gap will be the full square.
Yeah, it does. You know, in our definition, it does. I mean, we say that every region has a gap which is lower bounded by this delta, and so also the full region is lower by.
Right,
by
but
this
if I said like, oh, I'm only going to allow you to do that for squares as large as 3/4 n, would it imply? Would it imply? It would not imply a global gap condition, would it?
No. So these tilted squares could be pretty large, and that would still be an issue. So it's more about the alignment of the square with respect to the larger square. So they have to be well aligned, and then we're fine.
So
Nilan?
regarding this, can I ask if you are assuming that any sort of subsystem is gapped or just some structured ones?
Structured ones.
Yeah, in the proof we ask only for squares, for example.
Sorry, but they're structured with respect to the boundary that you're interested in.
Right. Yeah.
But if you had a boundary which was at a different different shape, then you would need a different structure.
Right. Yeah. Yeah. But I mean, we believe that this is really something technical that can be easily solved. I mean, it will not be too hard to generalize the proof for any shape of the cut.
But then once you want it for every shape of the cut, then wouldn't you need this local gap for every sort of subsystem?
Yeah.
Okay. Nilan had a question.
Does this local gap make more sense for frustration-free systems or than?
I think so. Yeah, I think so because in frustration-free system there is this this good overlap between the ground states, so it makes much more sense. I mean, I don't think it's very natural to discuss it. So actually, I think also the key for generalizing this proof to frustrated system is first to get rid of the local gap assumption.
So are you saying that there's no natural definition of local gap in once there's frustration?
Yeah, I think so. It doesn't. Yeah. I mean, if you have frustration, why should you have, for example, why should you have degeneracy of the ground states? But you must have degeneracy if you want to have something non-trivial globally, right? You must have degeneracy of local parts of the system.
You could do something like insist on polynomial number of states in a constant region, right? In a constant part of the spectrum.
Maybe that would be but but intuitively I think we can just get rid of this assumption somehow. I don't know how, but I think the conjecture is true also without this assumption.
Ramis and Nilan raised hands. Ramis.
Okay, so just a quick question. So to what extent do you need translational invariance, or to what extent, how do you make use of it in your local Hamiltonian? So you could actually just have locality and no translation invariance and everything should work. But like, I see. So yeah, you would expect the translation invariant case to be harder. I'm trying to see how does it get harder if you impose translation invariance.
Well, sorry, why would you say that it will become harder if you have translation invariance?
If you, for example, if you look at disordered systems, it's possible to have, it's easy to see that you could have, disconnected regions that have no entanglement. And So like once you impose translation invariance, things kind of become harder, which is I think the limit that you've succeeded in.
No, I'm sorry, I don't understand. I mean, in none of our proof did we ask for the Hamiltonians to be translation invariant.
So it
Right.
worked. Yeah, that's right. That's right. Yeah, so intuitively I would have thought, no, that's good. But intuitively, like for translation invariant case, the situation is harder. I wanted to see like if there was some intuition for why it becomes harder.
But wouldn't it be easier actually if you have translation invariant? I mean, wouldn't it be you have more structure in the system in some sense? No, I mean, you're more constrained, you're more limited. So I would have guessed that you have more handles in order to create a good AGSPs or to gain some understanding. I mean, it would be easier probably in that sense to analyze the structure of the system, no?
Well, if you have like random IID interactions, for example, and you have a local Hamiltonian, then it's not very hard.
You have random what?
Suppose you have random local interactions.
Mm-hmm.
All right, let's take them to be IID, then like independent identical distributed. It's not hard to prove that you can have regions or puddles, say rare local regions, that decouple from the rest of the system.
You mean like,
so in some sense, you can make use of probability theory to make statements very easily. Whereas when you have translation invariance, it's actually harder in my experience because of exactly what you said. This extra structure puts limitations on what you can use.
I understand.
But okay, maybe I should read your paper more carefully to see like, how you've done it. So I'm just trying to see, like how things would have become more difficult. I also had a quick comment about Norbert's statement. So if you go to really high dimensions, then mean field theory becomes exact. And, then trivially, I mean, things go to a product state. So trivially, your area law holds as well. So like these lower dimensional things, 2 and 3, are likely the hardest cases.
Right. Yeah.
It was a very nice talk and also a very nice tutorial before. Thank you, guys.
Thanks.
Great. I've put the gathered. Sorry, was there one other question, Anurag?
Yeah, Nilan had a question.
Yeah, one more question. Your 2D HSP in the other direction, so parallel to the cut, does it have volume entanglement? Or?
Sorry?
Does your HSP have full entanglement, volume entanglement in the other direction? Say the vertical.
Yeah. I think so, yeah. Yeah, because it uses, I mean, these parts here are very non-local. So if you cut it like that, you might have a lot of entanglement.
All right, thanks for a beautiful talk.
Thanks.
Great, thank you. So I put in the GatherTown link in the chat for anyone who wants to hang out and talk for longer. But thanks again, Itai and Zeph. This was really fun.
Okay, thank you, Miss.
Bye.
Bye.